Hello everyone. Today I'm the first to give you a topic about our approach of VRPTW. I'm Shibiao from Huawei Cloud. First, I want to apologize for using video like that. The network here is unsteady, and I hope this form can ensure you a smooth experience. So let's start. Our slides can be divided into three parts: the VRPTW background, the algorithm we use, and the experiment. First, I want to briefly introduce you the background of VRPTW. The vehicle routing problem with time windows is a generalization of the capacitated vehicle routing problem, where each customer is only available during a specific time window. First, please look at the right picture. You can find the time window in red number. And the right picture shows a possible solution of VRPTW with 4 routes. So let's look at the green ones. Here, 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 and here. You will find that the time window of each customer in one route will be larger and larger. Okay, let's move on. There are two widely used benchmarks in VRPTW. The Solomon benchmark is relatively small. It has 56 instances with 6 types. The customer number of each instance is exactly 100, and researchers also use the first 25 or 50 customers to create a small-scale instance and to compare results with each other. And the second one is the GNH benchmark. It has 300 instances over n equals 200, 400, 600, 800, and 1000, with also 6 types. You can calculate that the number of instances with specific n and a specific type is exactly 10. Okay, let's move on. Now let me tell you about the related work. The algorithms for VRP series can be divided into 2 categories: the heuristic and the exact. The former are dominant to the latter. And the state-of-the-art heuristic algorithms often employ the population-based structure and design effective recreate methods, and also local search operators to explore the neighborhood better. Here, I list some of the representative algorithms in recent years. First is the powerful route minimization heuristic from Nagata 29. It is a powerful route minimization. And second is also from Nagata, penalty-based edge assembly crossover, abbreviated as EAX. And then is the HGS from Vido 2013. It has a very good population management. And finally, the slack induction by string removals in 2020. It is a very good algorithm for many VRP series. Now, let's compare between traditional VRPTW and the new rule in DIMACS challenge. Researchers usually first minimize the route number and then the total distances for classic VRPTW, especially for the heuristic algorithms. However, the new rule asks to minimize the total distance directly, scored by a time-distance integral curve. And there is a notice. The route number of the optimal solution is usually larger than the minimum possible route number. So, if your solver gets stuck with wrong route numbers, it may have no room to improve the solution further. And this is the key for our solver. We propose a fast heuristic solver with dynamic root number adjustment. We employ the traditional population-based framework and local search operators, but we are iteratively increasing the population size to adjust the number of routes. So how to adjust? Let's first look at the examples. You can first focus on the clues. We fix the population size to 4, to 16th, and to 64. We just run the population-based algorithms once until all the solutions converge. And first, we look at this line for the instance with n equals to 200. And there is many colorful curves in the picture. The red one is the root number of the optimal solution. And you will find that it is enough to set a population size to 4 to quickly check out the optimal root number, because the red curve is exactly in the bottom. And also, if you enlarge the population size, you can get the similar result. And now let's move to 400. You'll find that it is not enough to check out the optimal root number if we just set the population size to 4. But if we enlarge to 16th, we will find that it is enough. And the 64 is also enough, but costs much time. And for customer number 600, we will find that if we set to 4 or 16th, it's both not enough to check the optimal root number. And only we set to 64, we will find that the red curve can be in the bottom. So what does this mean? Let's move on. We should keep an interval AOR to maintain the range of possible root numbers. And from the experiment above, we conclude that if the cluster number is small enough, maybe we can quickly track the optimal root numbers by setting the population size to 4 or to 16. But if the customer number becomes larger, it is difficult. Now, let me introduce some detail in our framework. At the beginning of program, the initial interval is set to L equals M and R equals M plus D, where M is the root number of a purple initial solution, and D is a hyperparameter determined by the data type, and we will introduce D in the later. So you can imagine that this initial interval AOR is something relatively big interval, and it includes all the possible root numbers. And then, at each round of population-based algorithms, the root number of each initial solution is selected randomly and independently from L to R. And the gap between AOR will gradually decrease in our control. There is a hyperparameter array maintained to control the length of AOR at different times. This length is typically 2 or 3 after the first round, and goes down and finally to 0. 0 means that L equals to R, and that means we have verified the optimal root number, and we just need to optimize our solutions with this root number. Okay, this is the total framework of our algorithms. The outside one is the time limit, and if the time limit T is not met, we start our new iteration of population-based algorithms. First, we construct many initial solutions with the root number in L and R. We will do this loop until all the solutions converge. And in this loop, we first shuffle the solutions we maintain in the members, and we take two solutions in each step and do some EAX, repair, and local search to find a good solution in the neighborhood. And if this solution can update the best solution, we just update. And finally, we will add this new solution to our members. Now, after this iteration, our members has updated. And we continue to this loop until all the solutions converge. And after this step is all done, we increase the num-p, the num-c, and the max-x. It means that we will enlarge the initial population size, the trying times in each iteration, here, and the max stagnation. And finally, we just shrink LR with the root number in our current best solution. Now let's move on. And now let me tell you something about our algorithm to accelerate the intra-root operators. Many researchers fail to make use of the property of intra-root case, which are special, well-structured, and sometimes time-consuming. And we combine all intra-root operators to execute local search together, separately from the inter-root cases. So there are two types of intra-root operators. One is the exchange and the other is the move. Exchange and the move. Exchange means we just exchange two customers U and V in the same route. And the move means we move one customer U forward or backward to the neighborhood of V, like that. Maybe this is U and this is V, and we just move the U backward to the neighborhood of V. And we add the parameter nsim to limit the distance of pairs in the same route. It means that if this route is very long, maybe we just need to do something in this length. Because if we want to exchange two customers here and here, it is almost impossible because these two customers, the time window of these two customers is really different. And now let me tell you some details. For the move case, we can try all pairs of customers in one route with time m multiply nsim by enumerating U and counting the previous or next nsim positions in order. It means that we first enumerating the customer U, and we continuously add a customer, and add a customer, and we just evaluate each step. So each consume time O m multiply nsim. And for the exchange cases, we apply the Vidal's technique to propose subsequence first, and the time complexity is still OM multiply nsim. So it is really quick. Okay, let's move on. Also, I want to tell something about the route minimization optimization. You may find it difficult to understand this slide if you don't read the paper from Nagata 29. We just improved the implementation in his paper. You know that the DFS of ejection is the most time-consuming part in Nagata's RM process. Let's recall the ejection. We use DFS to inject at most K customers. to repair the route and minimize the sum of penalties of ejected customers. We add a set SIK to record each possible sum-time pair when traveling to the ith customer with k customers ejected before. So the sum P means the sum of penalties of ejected customers, and the time means the current time. So when a new state is visited, first we will check whether there exists a pair sum time in SIK satisfying these two inequality. If there is a pair exists, it means that our new state is meaningless to DFS continuously, and we just close this DFS and return. And if no such pair exists, the DFS process will continue, and SIK will be updated accordingly. Now let's move to the experiment part. Some of our parameters are decided by the value of customer number n. For example, the number of neighbors considered for each customer n near. N near is used to control the neighborhood of each customer. Will be set to 10 if n equals to 100 and can be enlarged to 100 when n equals to 1000. So n near is proportional to the customer number n. And also some parameters are decided by the type of data. For example, the initial length of route number interval D is set to 3 or 10, depending on whether the type of data is 2 or 1. The 3 is corresponding to 2, and the 10 is corresponding to 1. Because the total demand queue in type 1 is smaller compared to the type 2, you can imagine that if the total demand queue is very small, so we will have more routes in the solution. So the number of routes becomes unsteady. So we just need to set the parameters 10. And I want to illustrate more about how to figure out the type of instance. We divide the plane into many equal-sized squares and count how many customers are there in each square. Then we calculate the standard deviation of those numbers to divide the data into 3 types: random, random cluster, and cluster. You can imagine that the random has the least standard deviation and cluster has the largest standard deviation. And the type of 1 or 2 can be simply identified by the ratio between the average customer demand and the limit of the total demand. Okay, let's move on. The proposed algorithm was implemented in C++, and the major parameters are listed in this table. You will find that many parameters are decided by the customer n, the value n near, the value n sim, the value non-fill, and d. We can run fast in the small data, and we can explore more neighborhood in the large data. For the results, we have won the second place over 12 teams in the first round, and I'm looking forward to the final results. And here is all I want to share. Is there any questions or any comments? Thank you.